Okay, let's start. Good morning. So this week is when we really switch over to calculus. So far, we were really looking at the substrate of calculus, set theory, continuity. Even though continuity is also part of calculus, it's so more souped up in a more souped up version. It becomes what is called topology. Calculus really starts with differentiating and integrating things. So we're going to switch to that, but we have some stuff that we need to talk about uniform convergence of sequences of functions, some other things. So I think at least today I'm going to take to discuss this, and possibly tomorrow as well. So I'm going to take attendance. Regarding the midterm, I'm very happy about the outcome. So the average is around like 86, I think. So that's an A plus, A minus. So that's pretty good. I have some critiques, of course. So one of the things that I thought was sort of like a general issue was that a lot of you were sort of rushing, especially the logical quantifiers. And as a consequence of that, you got confused about what you were trying to prove and what you had and stuff like that. So there's a reason why I'm spending so much time on logical stuff when I'm writing things. So even though it is cumbersome, it is at this level, I think it is very useful to be fast about writing logical statements and so on. Another thing that was somewhat worrying, not too much, but to some extent, was that I felt like most of you were not looking at the sort of feedback I was giving. So this and the form of sort of the problems from the problem sets that are graded for accuracy. So if you have sort of like a point deducted from a certain problem, typically, like if that problem was graded for accuracy, there's sort of like a detailed solution written on the solutions document. For instance, this idea of if a sequence converges, this guy converges, and then converges to 0, and then the other one is bounded, then the product also converges to 0. This was in problem set 3. It was a problem that was graded for accuracy. There were detailed solutions that I had put online on Wednesday. I mean, I sort of rushed grading this just so that we had sort of like an idea as to how to sort of look into this. And then even though many of you got this problem right, some of you did the following. You said, oh, I have the limit law. I know that the limit of the product is the product of the limits, and then therefore this is 0. The problem, of course, maybe I should ask you, what is the problem with that argument?
I feel like you can only make that argument knowing that the B sequence converges.
Exactly, right? So just because this guy is bounded, I don't know anything about it being converging. Of course, I can always sample out a convergent subsequence, but that's not what the question is saying, right? So imagine, this guy, what is a typical situation for this? X sub n is something like 1 over n, B sub n is minus 1 to the n, okay? What this problem is saying is that minus 1 to the n divided by n also goes to 0, which is true, of course. But you cannot use the limit law to get this, because this guy doesn't converge. Okay. You could have used lim sup and lim if you wanted, but maybe it is slightly more complicated. Okay. So when I'm sort of like grading a certain problem for accuracy, that should be like a signal for you. Okay, that's important. Okay. And in class 2, when I'm sort of slowing down about a certain topic, that should be a signal. Okay, I understand that we're talking about a lot of different things, but there are certain things where I slow down. Okay, that's a signal for you that this is important. Okay, so yes, that's it regarding the midterm. But overall, it's good. Now we can move forward. Are there any questions before I continue? Any qualms about the exam and stuff like that? Honestly, I was surprised by how many of you got confused about the first problem. I did not see that coming. That was actually a follow-up exercise in one of the in the solution document. So f to the minus 1 was is this idea of a pre-image, right? So we had talked about it. I had given you this idea, this parabola, right? So from -1 to 2 or something like that. Right? So something like this, and then we inverted it, right? So it's like becomes like something like this, blah blah blah. So if this is f inverse, and so on. That was based on this idea. So f inverse, this doesn't make sense in general, and it is also not the reciprocal. Okay, this is not the same thing as this. But anyway, in hindsight, I can see how this is like a confusing thing, because it's kind of abstract a little bit. Thank you. Anyway, I should also mention that I'm happy to discuss your previous work, even if a problem wasn't graded for accuracy. I'm happy to sort of go over your work and so on, and critique and so on, if you're willing to meet up with me. Oh, sorry. Yeah, there's an attendance sheet going on. Please make sure you sign it. Anyway, so that's all I wanted to say about logistical issues. Let's get back to math. Okay. So last time on Tuesday we had talked about this idea of convergence of a sequence of functions, right? And I mentioned there are two options at the very least. One of them is what is called pointwise convergence. The other one we said, oh, it's this uniform convergence. It's convergence relative to a certain metric, and so on. Now I'd like to go through all that stuff again, but I want to be a little bit more careful. Recall that when I defined this last time, I said there's an issue here. So I want to mention that as well. So this is how we start. I take two sets, arbitrary sets, x and y. These are abstract sets. And I take a metric d on the target set, on the output set. So d is a certain function, right? It has to satisfy certain axioms. But in particular, you can give to it 2 points in the capital Y space, or set. And d of those 2 points is supposed to be the distance. It satisfies the triangular inequality and all that stuff. And so this d sub c0, you should be able to use, I said, as a notion of distance between functions from x to y. So I feed to it 2 functions, and this is where things get complicated a little bit, because d itself is a function whose inputs are functions. In a sense, it's a functional, if you want. Okay, these kind of things happen all the time. So later on, we're going to see differentiation, for instance. The derivative operator is a function whose inputs are functions, and so on. And so what do? You take these 2 guys. You first feed to them the same point, x, and then now f of x and f of x and g of x are 2 points in y. And then using this metric that I chose, I can look at the distance between them, and then I can look at, I can optimize this distance. So this is in a sense the maximal vertical distance if you're trying to draw the graph of f and g. And so what is this? Perhaps you can write it like this as well. So what do? As x varies, lowercase x varies in uppercase x, this is a non-negative real number because d takes values in non-negative reals. So this is a subset of the reals, okay? Then I take the sup of that set. In exactly the same way that we have been discussing for the past couple of weeks, okay? So this is the value of a metric. No matter how abstract your space is, once you have a metric on it, everything turns into real numbers. And you can handle real numbers, ultimately, okay? The issue that I didn't mention last time was that technically, this function defined on all functions is not a metric because it can take the value infinity. Okay? So for instance, think of the following situation. Let's look at, so this x and y, let's take them both to be r. Let's say that f of x is 2x, g of x is 3x. Now the C0 distance between these two is infinity. Okay, and why is that? Because here's f, and here's g. I feed to them the same x, and I look at the vertical. Okay, so this d is the length of this vertical line segment. But I'm going to look at the maximal length I can get. But as you see, as I take x to be larger and larger values, the gap between them is going to keep growing ad infinitum. Okay? Which means that the distance between them is going to be infinity. Does this make sense? Now, for some people, this is a major problem. For some people, it's not. So technically, because of this issue, because this C0 metric takes infinity as a value, some people wouldn't want to call it a metric. Some people would, but some people wouldn't. And then they would say something like, oh, this is an infinite metric or something like that. But one thing we can do is we can look at the set of bounded functions from x to y. Then there are no issues, okay? So here's a new subset of functions. This is going to be a subset of the set of all functions. Namely, the subscript b says it's the set of bounded functions. So f, which f is a function such that its diameter, or rather the diameter of its image, is bounded. You're going to need this idea of a diameter for problem set 4 also. So let me remind you, I had defined this before, but so this notion of a diameter abstracts out the notion of a diameter of a ball. Okay? So how do you get the diameter of something like this? You take 2 points, and then you optimize. You look at the maximum distance between them. Okay? That's how you look at the diameter, how you define the diameter of a ball. That's one way at least. And so diameter of a subset is nothing but the sup of this set. y1, y2, where y1 and y2 vary in B. Again, this D is the same D as this. I take 2 points in Y, plug them in. Now it's a number. It's a real number. As I vary y1 and y2 in my abstract space, this gives me a set of real numbers, and then I look at the sup of it as a set of real numbers. Okay? So this is a set of bounded functions. This later on turns into something called the bornology, actually, this notion of boundedness. And here's an exercise. This function, d sub c0, when restricted to the set of bounded functions, is indeed a true metric according to our definition. So let me leave it here. Let me write it here. exercise. Is a metric. The hardest part of this is the so-called triangular inequality, which we had discussed, but it's a good idea to go through the computation again. It's a very nice exercise. Okay, so now we can define notions of convergence for function sequences. Now, instead of focusing on this, even though in this more general set of functions, this d sub c0 is not an actual metric, still you can talk about convergence. It's not really a major issue. And I'm just going to leave it at that, because this f sub b and so on, it gets somewhat technical as far as I'm concerned. I take two sets and a metric on the target set. And let's say that I have a sequence of functions from x to y, and then let's say that I have some other target function, f sub infinity. I'm going to say that f bullet sequence of functions converges to f sub infinity pointwise if the following happens. So f bullet converges pointwise to f sub infinity if for any x in x, the limit as n goes to infinity of the distance between f sub n of x and f sub infinity of x is 0. Okay? So I have functions that depend on, that has like this time parameter, but also a space parameter if you want. I fix one space parameter and I let time to infinity. And I want this distance to decay to 0, but I want it to happen for any x. Okay? Now, if you want to be more terse, what you can do is this. You can say f bullet of x. You see now, this is an expression that depends only on n, because you fed x to it already. For any x, this happens. This is like a more terse way of writing the same thing. I'm going to say f bullet converges to f infinity, while if their c0 distance go to 0. Okay? Okay. In a second, I'm going to open all of these up using epsilons and deltas. Now, the point is that this d is this d. The d is the metric on the target. For uniform convergence, you look at this C0 metric. Okay? Oh. In other words, f bullet is a convergent sequence that converges to f infinity in the metric space of functions. Any questions so far? These two look very similar, but they're very different. Okay. In a second, I'm going to mention an example, building on top of what we discussed already. Recall that we had looked at these monomials. We're going to get back to that in a second. But let's sort of write these down in using logical symbols to understand what is happening. Or maybe confuse ourselves even further. So for pointwise convergence, what do I need to do? I cannot change the order of the logical quantifiers, but I can just start opening up because I know what it means for any x in x, what the limit of this expression being 0 means, right? For any epsilon, there's a capital N such that after that capital N, blah, blah, blah. But I start with taking a lowercase x, then taking an epsilon. Now this is a sequence of real numbers, you see. This thing, once I fix the x, depends only on n. This is a sequence of real numbers. And I'm saying this sequence of real numbers converges to 0. How do I write that? Like this. There's a capital N that depends possibly on x and epsilon. So you can write it like this. Such that for any lowercase n after this uppercase n, well, what do I need to say? The distance between, so this number is less than epsilon. That's the content of pointwise convergence. The content of uniform convergence, again, I'm going to do the same thing. You see, this expression depends only on n. It has soups and blah, blah, blah in it, but this is a function of n. In other words, this is a sequence of real numbers, and I'm saying that I want this sequence of real numbers to converge to 0. Okay, how do I write it? You see, I don't start with for any x now. I need to start with for any epsilon. For any epsilon, there is an n that again might depend on epsilon, but it doesn't depend on x because I didn't choose the x before. Okay? That's the major difference. Such that for any n after this capital N, this value is less than epsilon, but this value is sup of something. Sup of something being less than epsilon means that for anything in there, in that set, I have that bound. So I can write it like this. Okay, they look very similar. They are very different. I mean, they are related, of course, but. Now, what is the main difference here? The main difference is the position of when you choose the lowercase x. Okay, everything else is the same. And that's why I'm suggesting that you keep writing these quantifiers, carefully until you get the hang of it. Once you get the hang of it, you can just, hand wave a bunch of things, but you see, this guy being here is different than this guy being here. That's the only difference. Yes?
Is converging uniformly like a stronger statement than pointwise?
Exactly. Yes. question. And in fact, that was the first thing I wanted to do. So uniform convergence is stronger than pointwise convergence. Let's see what that would mean. Oh, so let me also say a couple more words. If f bullet converges pointwise to f infinity, then you say that f infinity is the pointwise limit of the sequence. And if it converges uniformly, you say that this guy is the uniform limit. Okay? Why the word uniform? Well, the idea is that in pointwise convergence, you have this time n, right? That possibly depends on x. In uniform convergence, you again have this time n, after which you have this bound, but that works for any x. So this guy works uniformly in x. That's the idea. Same time works for all n. Okay? Of course, the statement is that you can't find a time like that. It is not necessarily true that the time that you were looking into that works pointwise works uniformly, but maybe you can find a different time that works for all time, all x. Okay, so the idea is that uniform convergence implies pointwise convergence. Okay? So it is something stronger. Claim in the same setting as the definition. So I have two sets, x and y, and there's a metric d on y, so that I can talk about the C0 distance. If f bullet converges to f infinity uniformly, then it also converges pointwise. In general, the other way around is not true, okay? Still, this is important. So let's prove it. Now I'm assuming that f bullet converges to f infinity. So suppose f bullet converges to f infinity uniformly. What do I want? I want that f bullet converges to f infinity pointwise. AKA, for any x in x, I want this to happen. Okay. So let's let an x in x. Let's also let an epsilon. I don't even need to care about this x here, okay? I can say, I can take this epsilon that I chose. I can use it here, because I know that f bullet is convergent uniformly to f infinity. There's a capital N that doesn't depend on this x that I chose, but it is there, such that after that I have this bound. That works for any x. Maybe I should be a little bit more explicit. Let's say this is x star. For any x star, this happens. Since f bullet converges uniformly to f infinity, there is an n that depends possibly on epsilon, such that after that n, and for any x, I have the bound well, if this bound holds for any x in x, it in particular holds for this point that I started with. Okay? In particular, if I were to choose this arbitrary x to be x star that I started with, the same bound holds, which literally means that this sequence of points in y converges to that point, which is the end of the proof. It's not very deep, but it can become confusing, these logical statements. Okay. So here's an alternative proof that is slightly more slick, but it requires some more compression. So alternative proof. Again, I'm assuming that I have uniform convergence. I want to show pointwise convergence. Then this is the sequence of real numbers that I want to bound. Well, because d is a metric, I know that this is bounded by 0 from below. And from above, if I were to take the suprema over the, or supremum over the inputs, this would turn into the C0 distance. By assumption, I know that this sequence of real numbers converges to 0. And by the squeeze theorem, that means that the middle term also has to converge. That's another way of doing the same thing. Okay. So you see, math is all about like finding these higher order data structures, in a sense, that allow you to sort of, instead of looking at epsilons and deltas, put everything into this more complicated object. In a sense, the definition is more complicated, but using it is slightly more convenient if you know what you're doing. You end up needing to write less things down. Any questions about these? Now, as a consequence of this claim, we have this very important thing, namely that the uniform limit of a sequence of functions, if it exists, it also has to be the pointwise limit. Okay? And so this also gives you an idea as to how to find the uniform limit of a sequence of functions. It says, first find the pointwise limit, and then see if that pointwise convergence can be upgraded to uniform convergence. Okay? So let me write that down because this is important. I should also mention, for instance, because f bullet converging to f infinity uniformly literally means convergence relative to a metric. By one of the exercises I had given you a while ago, we know that limits in any metric space are unique, which means that a sequence of functions cannot converge to multiple functions uniformly. There's a unique, if it converges, there's a unique limit, and so on. So, in particular, if f infinity is the uniform limit of f bullet, then it is also the pointwise limit. Hence, to see if a sequence of functions converges uniformly, in other words, if it has a uniform limit, what you can do is you can first look at whether or not it converges pointwise, and then see if that convergence can be upgraded to uniform convergence. Okay, so this is something that you do all the time in analysis. Instead of going for the stronger thing, you first go for the weaker thing, and then you do some magic, if possible, to upgrade your statement. So to find the uniform limit, first find, it may fail to exist, of course, but that's the first step, is what I'm trying to say. First find the pointwise limit. Then see if convergence can be upgraded. Can be upgraded. Any questions about this? Here's a nice exercise. How many of you have heard of this term, delta function? Okay, yeah. If you're doing physics, you've heard of it. Really, this claim that uniform convergence implies pointwise convergence is the statement that delta functions are continuous. Okay, I'm not going to do this, but it's an exercise. Let's write it like this. Let x star be a point in x. Same setup. I have two sets, x and y. Y has a metric d on it, so that I have the C0 distance. What I'm saying is that delta sub x star from the set of all functions from x to y that takes a function f and sends it to f of x star is continuous. What does it mean for delta x star to be continuous? Well, this is a metric space. This is a metric space. I'm saying that if you have a sequence of functions that converges here, the endpoints, the targets also converge. This is just like an upscaled restatement of this claim, actually. The exercise is to realize this. is the same as the above claim. Okay. Physics, it turns out to be important in electronics and stuff like that. So this sort of like represents sort of like a localized sort of impulse. Very important in differential equations, other things. Okay, so any questions? In engineering and stuff, you would see instead of this, you would see this. You want to think of it as an integral. This is kind of like a bizarre thing, and like it's the same notation. It's the same idea, different notation. Okay, so the example I would like to give is the following. Same example that we discussed before, but it's the fundamental example, okay? I'm going to take a row between 0 and 1. Could be 1, but it's going to be positive. Let me let f bullet to be a sequence starting at time 1, taking values in a set of all functions from the closed interval 0 to rho to reals. At time n, I want my function to take x to the n. It's like a functional notation. And then let me define f sub infinity to be 0 if x is less than 1 and 1 if x is 1. The claim is that f bullet converges to f infinity pointwise but not uniformly if rho is 1 and if rho is less than 1, then f bullet converges to f infinity uniformly as well as pointwise after this. Okay. Now in the remaining 5-6 minutes, I would like to understand what is going on here. Okay. We have discussed, I guess, the first item, right? So because we were trying to understand the sequence of functions, what we did was we drew the graph, and then we took vertical sequences to get the limits, right? But then we realized that, okay, so this guy converges to this, vertically speaking, but the limit is not a continuous function, and that was an issue, right? This is the main reason why we're doing all this stuff. I'm going to take a part of tomorrow's class to discuss this, but the whole point behind these different notions of convergence is that because under pointwise convergence, the property of being continuous is not preserved, but you want the limit to be a continuous function also, okay? So instead of looking at pointwise convergence, you look at this stronger idea, stronger concept. So here's the graph. So they all start at 0. They all end up at 1. Okay. When n equals 1, I have the diagonal function. Assume that this is diagonal. And then when n equals 2, I have the parabola. Then I have the cubic, and then quartic, and so on. Let's do one more. Quintic. Okay. So what is the f infinity? How does it look like? And we have green here. F infinity is this function. It has a discontinuity, right? Because when you're converging to this guy, you see the value jumps. So why am I saying that f bullet converges pointwise to f infinity? Well, I take an x here. I'm going to have to do this for any x, but we start with 1x. You look at the vertical. Okay, and you record all of these heights. Right, so this is f sub 1 of x, this is f sub 2 of x, this is f sub 3 of x, and of course f sub infinity of x we defined to be 0 because I'm taking x to be somewhere in between. Okay, and when I look at this, well, the sequence converges to 0. That's why this is converging pointwise. Okay? You look at this convergence. So this sort of like this is the abstract x space. It's always horizontal, imagine. And the abstract y space is always vertical. Of course, you cannot always draw it like this, but this is the caricature. Now, it doesn't converge uniformly. How do I see that? Well, here's how you see it. I take an epsilon ribbon around the limit function, right? That was the idea. So you take plus epsilon minus epsilon. What I need is the following. After finite time, the graph of f sub n has to be inside this epsilon ribbon around the targets. That's what it means for f sub n to be epsilon close in C0 metric. But you see, this never happens because for any n, because eventually they're going to end up here by the intermediate value theorem or whatever, I can take this height, and there's always going to be one point outside this ribbon. Okay? I'll mention this again tomorrow. This is a very important idea. But it's hard to sort of come to terms with all this stuff. It's complicated, but it's very important, and this is the fundamental thing, one of the fundamental things you're going to get out of this class. So I want to take more time on this. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today I'd like to spend more time on this uniform convergence of a sequence of functions. We had discussed how, I had mentioned it a couple of times, that although the pointwise limit of a sequence of continuous functions may fail to be continuous, if you have a uniform limit of a sequence of continuous functions, then that limit is going to be continuous. So we're going to state it formally and prove it. But before that, this was our important example. I want to spend more time on this. So here's the situation, right? So I take a row. That's a parameter. It's between 0 and 1. Depending on what row is, the behavior is going to be different. So I fix a row, and then I define a sequence of functions, which are the monomials. Okay? And I have this function, f sub infinity, which is defined like this. So I take an x to 0 if x is less than 1, and 1 if x is 1. And of course, if rho is less than 1, then this is just a constant function 0. Okay? It's just that this description works for both cases, for rho equals 1 or rho less than 1. Okay? So what do we want? We had talked about this, that f bullet converges pointwise to f infinity. And how did we do that? Well, you fix an input value. In other words, you fix a vertical, right? You take a slice that gives you a vertical sequence. Let's say this cross section, let's say, and then you look at these points. That gives you a sequence that converges to f infinity, f sub infinity of x. So that's pointwise convergence. And why is this sequence not uniformly convergent? Well, in order for uniform convergence, recall that we need to have, so for uniform convergence, need the C0 distance between these two functions to be less than epsilon for large n, right? For sufficiently large n. Graphically speaking, what does this mean? I look at the graph of the target function, right? I always find the target function by looking at the pointwise limit, and then I look at whether or not it can be upgraded to uniform limits. So let's say that my function, my limit function is f infinity, and let's say that it looks like this. Okay, this is my f infinity. Then, to understand this, what I do is I look at an epsilon ribbon around f infinity. So I'm going to look at the value of f infinity plus an epsilon or minus an epsilon, and I'm going to sort of sweep using that those bounds. So it's going to be something like this. So let's start here, for instance. Let's say this is plus epsilon, this is minus epsilon. So I have a candle. Okay? So I'm going to keep moving this candle in such a way that its center is always on the graph of f infinity, and its length is 2 epsilon. Okay? So I'm just going to sweep it like this. So approximately it looks like this then. Okay? So this is plus epsilon, this is minus epsilon. In order for the sequence f bullet to converge to f infinity, what I need is that after finite time, in other words, for sufficiently large n, I need the graph of f sub n to be inside this ribbon. All of it, okay? That's the thing. And as I increase n, quite possibly the function is going to change, right? That's the point. But no matter how it changes, I want it to be stuck in this epsilon ribbon. And this works in higher dimensions too. But of course, for us, it's not going to be important that much. This is already too complicated, as you see. Functions, single variable functions, or understanding the space of continuous functions with single variables is already sufficiently complicated. Okay, so this requires, so this is the picture for uniform convergence. So what do I need to do? I need to look at the epsilon ribbon around the limit function. So my limit function is the green graph here. So plus epsilon minus epsilon, right? And it goes like this. You don't include this point. You don't include this point. But there's a candle here. So now in this picture, of course, I drew f infinity to be a continuous function, and then the ribbon came out to be a nice sort of shape as well. But in this case, the limit function is not continuous, so the ribbon also is not continuous. Now note that even though you have pointwise convergence, if I choose epsilon small enough, let's say 1/2 or something, then in fact none of these functions, f sub 1, f sub 2, f sub 3, is going to be completely inside this ribbon because they're stuck here. Okay? Is this sort of making sense a little bit?
There's the intuition.
Yes, okay.
I'm struggling with uniform convergence for a little bit.
Yeah. Now, how could you say this? For instance, you could say, let's let epsilon to be 1/4. Then 1/2 is somewhere here. I know that each of these monomials are continuous functions, which means that by the intermediate value theorem, they attain the value 1/2 at some point. And I also know that because they're strictly increasing, one of the other theorems gives me that they're homeomorphisms. In other words, each of these monomials attain the value 1/2 at exactly one point, which means that none of these functions have graphs completely inside this epsilon equals 1/4 ribbon. Therefore, it is not uniformly convergent. Okay, so this is the argument. I'm not going to write it down, but it's a very good exercise for you to sort of slowly think about this, write it out, and so on. Okay, so but what happens if I switch rho from 1 to some number less than 1? So here I drew the same picture. The point here is that now we have something like this, right? So rho is somewhere here, so I'm getting rid of this part of the picture. So this was the rho equals 1 case. Now this is the rho less than 1 case, maybe 1/2 or something. Obviously, it doesn't matter what the exact value of rho is. So somewhere here. Now see what happens. In this case, my target function becomes the function that is constantly 0. Okay? And each of these, none of these monomials actually reach the 1 because I'm cutting the graph before that happens. Right? So this height is going to be exactly rho, for instance, because this function is supposed to be the diagonal function, and then this is like, what is it, rho squared and so on. Okay. Okay, so I can look at pointwise convergence like I did before, and that's how I really came up with this target function. But let's see if this converges uniformly. I'm saying there it does, but it should match with our intuition. So again, I'm going to take an epsilon ribbon around it, right? There's something like this. Okay. Now, because the limit function now is constant, my ribbon is going to be a rectangle, of course, whose one side is 2 epsilon. Well, it doesn't seem like this works actually, because for instance, if I were to look at this function, or even this function, x cubed, its graph is not inside the ribbon. But is that an issue? Right? The point is, I need to wait longer. Depending on the epsilon, I'm going to need to wait longer. Right? So if epsilon is 1 over 4, depending on the value of rho, if I wait long enough, I know that as I take n to be larger and larger, this function is going to become flatter and flatter. Right? That's the whole point. In other words, ultimately, this is the graph of this f sub n is not going to be able to escape this ribbon. Now, in this case, we're not using sort of the lower part of the ribbon, but this just happens to be the case. I mean, in single variable calculus, we don't really distinguish between, undershooting and overshooting that much because you're looking at the absolute values after all. But ultimately, the point is that each of these f sub n's are going to have graph inside this epsilon ribbon. And that's why this is uniformly convergent. Okay. Any questions about this? Yes.
So, just to be clear, the reason that it works for rho less than 1 is because there is, like, the ribbon doesn't go up arbitrarily to, like, infinity at that 1 point, rho equals 1 point?
I mean, ultimately, yes, but you want to say, perhaps you want to think of it like this. I want to keep shrinking the ribbon as much as possible.
Okay.
But the point is that it's not that the ribbon sort of jumps here. Mm-hmm. That's not the issue. The issue is that these functions don't jump up there. Yeah. But yeah, I mean, ultimately, they're probably underneath, they're the same things. Yeah, so. Because ultimately, because I'm going to keep taking epsilon smaller and smaller, that's sort of the heuristic, instead of sort of, yeah, I mean, yeah, I guess what you're saying is correct. It's an equivalent way of saying the same thing, I think, yeah. Okay. Any other questions? Now here's the important theorem. If I have a sequence of continuous functions that converges uniformly, then the limit itself is also continuous. Now note that so far we were looking at the situation where we have a capital X, capital Y, so the input space, output space. Only the output space had a metric on it. But in order to talk about continuous functions, I need a metric on the input space also. Okay, so that's sort of like an extra structure I need at this point. So far, I actually didn't need it. Of course, for this example, I did need it because I wanted to talk about continuity. But if you're looking at abstract situations, it's a good idea to always keep track of what is needed and what is not needed in terms of structures. So theorem. Let X and Y be two metric spaces. So that I can talk about continuous functions between them. Let's let f bullet to be a sequence of continuous functions. And let's also, okay, I'm just going to leave it like that actually, yeah. F bullet be a sequence of continuous functions. F infinity be a continuous function. Oh, sorry, f infinity some arbitrary function. I don't know the continuity of it. If f bullet converges uniformly to f infinity, in other words, if f infinity is the uniform limit of the sequence f bullet, then in fact this function is continuous. So while pointwise convergence may not inherit continuity properties, like we saw in this case, uniform convergence does. Okay? So I have a bunch of things. I have that for each n, f sub n is a continuous function. And I have that f sub n's converge to f infinity uniformly. And I want that this function from x to y is continuous. Well, in order for a function to be continuous, it has to be continuous everywhere, which means that I need to fix a base point. So let x star be in x. Want, well, f infinity is continuous at x star. Any suggestions as to how we can continue? There are two basic methods, right, to show continuity of a function. Either we're going to use epsilon delta or we're going to use sequences. Which one should we try? They're ultimately the same proof in this case, but maybe the formalism is slightly different. We can use sequences to get this, or epsilon delta.
Epsilon delta?
Okay. So how do you do the epsilon delta proof? You let an epsilon, and then you try to bound something, right? So that is, so let's write it out explicitly using epsilon delta. What we want for any epsilon positive, there's a delta positive such that for any x in x, if the distance between x and x star is bounded by delta, then the distance between their images, f of x and f of x star, is bounded by epsilon. This is what I want. Okay. So let's let an epsilon be a positive number and see what we can do. When you're first learning this, all this stuff, this looks like something, I don't know, perhaps hard to think about. But ultimately, there is, in this context, pretty much one trick, okay? Maybe you have an idea as to what the trick is. So let's let epsilon to be a positive number. I want to bound this guy. How can I bound this? By epsilon, or by some number. Think of it like this. How can I control this guy? Using what I already have. Oh, of course, this should be f infinity here. Well, you have a couple things, right? You have that each of these functions is continuous, and that you have this uniform convergence. Well, let's do this then. The trick in these situations is always, almost always, let's say, triangular inequality. Okay? So triangular inequality is something that produces upper bounds, right? So, and I'm trying to upper bound it. So in a sense, it looks like it's not something that should work, because ultimately you don't want to increase this thing. But if you can upper bound it by something that can be bounded, then this guy is also bounded in a sense, right? So what I can do is I can inject a term f sub n of x into this, and then this would grow. I'm going to worry about the quantifiers later. Okay, Now, why did I inject this guy into this thing? Well, because I know that this is bounded by the C0 distance between f sub n and f infinity. That's why I fed it the same point. Okay? So this I have control over. I know that as n goes to infinity, this is going to decay to 0 by uniform convergence. But now there's an issue, which is this. How can I control this guy? You see, because I cannot use uniform convergence here immediately, because the input has to be the same value. Yes?
Shouldn't the symmetry axiom be helpful here, where you just flip them around?
Maybe, but if you were to flip this around, again, it's the issue. The same issue remains because you're not using the same input. You need to use the same input for the C0 metric.
Oh, that's all right.
Well, what you can do is you can apply the same trick. Now inject into this f sub n of x infinity. Okay. So I have this term. Plus, now this is going to grow into f sub n of x, f sub n of x star, plus f sub n x star, f sub infinity x star. Okay. Now, why did I do this? Because ultimately, I'm thinking the following. This I have control over because I have uniform convergence of f bullet to f infinity. And for the same reason, this. Now, I have this extra annoying thing. But this I have control over also because I know that each f sub n is continuous. So if I take x sufficiently close to x star, I'm going to be able to control this guy also. So I started with this guy, and I upper bounded it by expressions that I feel like I can control. And so what can I write here? So this is bounded by the C0 distance between f sub n and f sub infinity, and likewise there. So I have twice the C0 distance. Plus this guy. Okay. Any questions so far? I just applied the triangular inequality and the definition of the C0 distance. Right, so this guy is bounded from above by this, and likewise this guy is also bounded from above by the same expression. So I have twice this expression, plus I have the middle term. Okay. Well, now what I can do is this. I can say, because f bullet converges to f infinity uniformly, I have that there is some capital N such that after that, really, I can say that this is bounded by, let's say, epsilon over 4, because ultimately, I want to bound this expression by epsilon so that this guy becomes bounded by epsilon. Such that the C0 metric, the C0 distance between f sub capital N and f sub infinity is bounded by epsilon over 4. So this gives me control over this. But furthermore, I know that f sub n is a continuous function. In particular, it is continuous at x star. And so that gives me that there's a delta such that I can bound this for f sub capital N. And for any x in x, let's say, if the distance between x and x star is bounded by delta, then the distance between their images under the nth term of the sequence is bounded by epsilon over 2. Okay? So here I had all the freedom about which index n I was going to use, so I might as well choose that n to be this capital N that I have. And so let me just update this. So that ultimately what I have is that this is bounded from above by epsilon over 4, and this is bounded from above by epsilon over 2. So this is the red bound. And then this is the blue bound. And they add up to epsilon. Okay. So given an epsilon, I was able to find a delta such that for any x after, so for any x in x, that is delta close to x star, I have that this is bounded by epsilon. That is what I wanted. And that's the end of the proof. In other words, this f infinity is continuous. Questions about this? So when you're trying to write proofs like this, start from the end. Start from what you want. Okay? Typically, when it comes to metrics and stuff like that, the one trick is always to use triangular inequality. Now keep sort of injecting terms into this to get sort of like a possibly larger term, but still you want to get things that you know you can bound based on the assumptions you have. So I have the assumption that each f sub n is continuous and I have uniform continuity. Any questions about this? Analysis is a little bit paradoxical because when someone else does it in front of you, everything looks obvious, and then you see it, you encounter something on your own, and then it turns out to be not that straightforward somehow. But in time and in experience, you're going to be better at these kind of things. Of course, it's a very nice exercise to do the same proof, but with sequences. So take an arbitrary sequence in X converging to X star and try to show that the image of the sequence under f infinity converges to f infinity X star. So I'm going to leave that as an exercise. It's the same trick ultimately. So exercise. Prove using sequences. Okay. I'm also going to leave it as an exercise to show that if I had a sequence of continuous and bounded functions, then this limit, if let's say that if converges uniformly, then the limit is in the set of continuous and bounded sets, bounded functions. So that's an exercise also. Now there's a more concise way of sort of summarizing this situation. You can say that the subset of continuous functions from x to y is a closed subset of the set of all functions. Okay. C0 xy and C0b set of continuous and bounded functions are closed subsets relative to the C0 metric. This is literally the same thing as saying this. Now, what is the definition of a closed subset? Here it is. As part of a bunch of definitions. We're not going to use them too much, but it's good to come to terms with these notions. I had said that continuity really is not that much about calculus, but really is about a field called topology. Topology literally means the knowledge or study of space. Topos means space in Greek. And so if you keep taking classes, ultimately you're going to end up needing to take a topology class as well. And so these are really about, these notions come from that field really of mathematics. Compactness also came from that. And if you're going to take the SQL class, you're going to spend a lot of time on these notions. But for now, I think just the definitions is going to be sufficient. Let X be a metric space, a subset U is closed, is open, sorry, if for any U in U there is an epsilon positive such that the open ball centered at U of radius epsilon is inside U. And you're going to see this open ball notion in problem set 4 also. I mean, if you started looking into it, you have already seen it. So this is an open ball of radius epsilon centered at U. That should be X, U, sorry. U. And I'm going to call a subset F closed if this happens. What does that mean? Well, I need to take a sequence in this subset that converges to some point in this larger space X then I want that limit to be inside the set already. So if for any, let's say, x bullet sequence in F, and for any x infinity, if x bullet converges to x infinity, then in fact x infinity is in F. Okay. Some exercises about this. Somehow the notions of closed and open subsets are complementary, in the sense that a subset F is closed if and only if its complement is open. X take away F, which is F to the C complement, is open. If I have a compact subset, then it is also closed, something weaker than compactness, this means. And here are the standard examples for us. Well, closed intervals are intervals that are closed in this sense. Open intervals are intervals that are open in this sense. So this is closed, 0 to infinity, also closed, 0, 1, open is open. Half open, half closed intervals are neither. And the real line itself is both. Okay. It takes a while to get accustomed to these ideas, openness and closeness, that they are very useful. And no matter what type of math you do, you end up doing, you're going to probably need it eventually. So, in single variable calculus, perhaps the functionality of these notions are somewhat limited, although not exactly really. But still, it's good to know. Any questions about these? Yes?
Sorry, what is a ball?
That is the definition.
Oh. Like what would be like a, kind of more like a physical understanding?
In the Euclidean space, relative to the Euclidean distance, a ball is a ball.
Okay.
Yes. So how do you define a ball? You say you have a center, and I'm looking at all the points that are not more than epsilon away. So that's an epsilon ball. Okay, so this is the beauty of using metrics. You see you have this function that satisfies the triangular inequality, and somehow just having this allows you to talk about balls, spheres, and so on, which allows you to do geometry, ultimately. Yeah. In dimension 1, of course, this just becomes an open interval, because you only have one dimension after all. Any other questions? Okay. So here's a theorem that I'm not going to prove. I'm just going to mention, because in the textbook they talk about this sequence of functions that is uniformly Cauchy. We didn't spend that much time on Cauchiness. So Cauchiness, we said before, is about sort of volatility. Cauchy sequences are non-volatile, asymptotically speaking, sequences. And in many cases that we're going to be interested in, that's going to be equivalent to just convergent. So that's why I'm not spending that much time. But I'm just going to state the theorem. And maybe later on, if we have some time, we can discuss this completeness and Cauchiness and all that stuff that I skipped altogether. So let me let x and y to be two sets, and let's let d sub y to be a metric. In fact, let's just take metric spaces to begin with. Let x dx, y dy be metric spaces. Then y, let's write it like this, dy is complete. In other words, any Cauchy sequence in y converges to some point. If and only if the set of all bounded functions from x to y with C0 metric is complete. If and only if the set of all continuous and bounded functions from x to y, again with the C0 metric, is complete. Very useful theorem, but we're going to skip the proof of it. So whenever we're encountering things like uniform continuity, Cauchy sequence, complete metric space, these ideas are sort of distributed in the textbook, but they are not quite the same at the same level as continuity, really. They're really sort of like a different beast. That's why I'm sort of separating them and not spending that much time. So in particular, this means that no matter what x is, the set of bounded and continuous functions taking real values is complete, because reals is complete, okay? In particular, so I don't need to write b there. The set of continuous functions taking real values defined on the unit interval 0, 1 is complete. Okay. Important stuff, but we have more important things to talk about, so I'm going to not spend too much time on this. Any questions? Now we have one final thing to discuss toward differentiability, which is the notion of a limit of a function at a point where it is not defined. So I need something like this. I need some formalism to distinguish different types of behavior in the boundary. Okay, so here's sort of like here's the type of functions that I want to be able to distinguish. So want to be able to distinguish these three things. Let's say maybe this guy is f of x equals 1 over x defined on 0, 1. Well, in this case, you have an asymptote, right? So you start at 1, then you have an asymptote. But maybe f of x equals 1 on 0, 1. You see, technically, even though I could define f of 0 to be 1 here, and everything would be fine, it is not quite defined there. It's a gap, so there's a gap there. But certainly, even though neither of these functions are defined at 0, the behavior of this is different than the behavior of this, right? So the asymptote of this is infinity, or rather, this goes to infinity, whereas this converges to the value 1 as I take x to 0. And then the third option is something like, well, you're going to see this function in problem set 4, or something like this. Well, this is something that again is continuous, where it is defined, because it's a composition of continuous functions. But at 0, something bizarre happens, because as you take x closer and closer to 0, this starts oscillating faster and faster, okay? So at 1, it's going to be sine of 1 is some number that is very small, but then ultimately, this is what happens. Okay, it keeps oscillating faster and faster. Now, these three functions, neither of them technically are defined at 0, but their limit as x goes to 0 are different. So their behaviors are different. I want to be able to distinguish them in a formal manner. Okay. You have 2 minutes. Okay, let's try it. May not be able to finish it today. So definition. Now, what do I need? I need a metric space, and I need two metric spaces. So the horizontal metric space, vertical metric space. I need a subset on which my function is defined, and I want my function to be continuous there, but that is not really that important. And I want to be able to approximate this point using sequences, using points in my domain. Right? So that's the situation in all of them. Okay, so this, okay, I'm not going to push it, but this is the idea that we need to sort of extract out. We're going to do this tomorrow, and then we're going to start talking about differential calculus. Thank you. I'll see you tomorrow. Okay, let's start. Good morning. So today is very exciting because we're going to start doing calculus, really. We're going to start with differential calculus. And this weekend, so the rest of this week and next week, we're going to be talking about differentiability, differential calculus, some nice things, mean value theorem, inverse function theorem, and so on. But we have this final item remaining. In the textbook, this is actually part of the chapter about differentiability, but still. And this idea of the limit of a function at a point where it doesn't necessarily exist, where it's not defined, right? So yesterday we were talking about something like this. We had, for instance, 1 over x defined on 1, 0, which had a graph like this, and then we had, I don't know, let's say constant function 1, which was like this. And then we had sine of 1 over x, which looks like this. So I'm thinking of these to be defined on the half open, half closed interval. This I have to define it like this, but I can take the constant function to be on this as well, and so on. The point was that even though neither of these functions technically are defined at x equals 0, because I'm just discarding that point from the domain, the behaviors are different. And so somehow we were trying to extract out this idea. So even though, for instance, 1 over x is not defined at 0, how can I make sense of this asymptote, right? And so this is the formalism behind it. I'm going to take two metric spaces, x and y. I'm going to take a subset A, and 2 points, x star and y star. X star in x, y star in y. And I'm going to take f to be a function defined only on A. Now note that at this point, I'm not saying anything about whether or not x star is a point in A. So maybe f of x star is well defined, maybe it is not well defined, okay? So for instance, in this case, so you should think of x star as 0 for all 3 examples here. And so you see f of x star here is not defined as a real number. Here it is defined, but I'm not considering it. And this is my A. Now here's this assumption. This is a new symbol that I'm going to define in a second. Basically, this expression represents the idea that, oh, this x star point is not necessarily in A, but I can approximate it using points in A, arbitrarily closely, okay? So I'm going to give you the definition of this symbol in a second, but this is what that means, that I can approximate x star using points in A arbitrarily closely. So x star has to be near A in a sense. Then we say that the limit of f at x star along A, so this is the new term, is y star if the following happens. Okay? So for any epsilon, there's a delta such that for any A in A you see, not in A in X, A in A in this restricted subset, if A is delta close to this limit point, let's say, x star, then the images, well, f of x star is not necessarily defined, you see, but I'm just taking this other value. I want f of A, the image of this point, which I know is well defined, I want it to be epsilon close to y star. And in this case, we write this. Instead of just putting it like this would be like the standard limit. I'm saying, oh, I'm taking the limit along A. Okay? So that's the definition. It's not really too sophisticated. It just requires a little bit more sort of math literacy to understand. So once you understand epsilon delta, it's not sort of like a major deal. So here's the definition of this symbol. If you have a subset in a metric space, putting a bar on top of it represents taking its so-called closure. So you take a subset, maybe it is not closed under taking limits. Well, you add all the limit points in, that gives you the closure of the set. Okay? So definition. Be a metric space. A be a subset. Its closure is, by definition, how should we write this? Let's write it like this. So A bar is A union, well, all limit points of all sequences that can be written in A. So let's say x infinity in X such that there's a sequence A bullet in A that converges to X infinity. Okay. To connect this to the terminology that I introduced yesterday, a subset is closed if and only if it is equal to its closure. In other words, somehow any limit point is already in A. So this is sort of like a redundant union. Okay. So this is like a nice idea. And here's an exercise that is related to this, which really tells you that this is nothing new. Well, the limit of f as x goes to x star along A is y star, that definition. If and only if, well, f has this extension, f tilde. So I don't know if x star is in A, but in any event, I can take this union. Now this is a slightly larger set, quite possibly. And I can look at this function that takes an x and sends it to f of x whenever it is defined. And if it is not defined, in the case x star is not in A, then I'm just going to define this function to have value y star. And I want this to be continuous at x star. So saying that this limit exists like this is the same thing as saying that this extension is continuous at this point. Okay. It's a nice exercise. This is just like a paraphrase ultimately. Nothing too deep going on. Any questions about this? Now, applying this to the single variable setting, in particular, let's say if you have a function that is defined on the real line or on an interval or something, what we can do is we can look at left limits and right limits. Okay? So we can take a point and we can try approaching it from this side or from this side. In one dimension, this is allowed. In higher dimensions, in abstract metric spaces, this obviously doesn't make sense. But if we have single variable, then this is perfectly valid. So let's say that I have this time an open interval, lambda rho. In fact, I can allow lambda and rho to be a minus or positive infinity in this case. And let's say that Y a metric space. It could be reals, it could be whatever. That's not really important. And let's say that I have a function defined on I. It could be any function. And let's take a target value, y star. So what is the situation here? Somewhere here is lambda, somewhere here is rho. F is not necessarily well-defined on the boundary, but in it, it is well-defined. So this is I. There's a graph here. And I have a height, y star. Well then, instead of writing, how did we write it? So x goes to, let's say, rho, x in I, okay, f of x. So that means that I have my function here, let's say something like this. The function doesn't need to be continuous, but let's just draw a continuous function. Well, as I'm taking points closer and closer to this point, I'm getting this value, right? So instead of writing this, this is equal to y star. So that y star should be somewhere here. Instead of writing this, there's a couple different sort of easier notations. Is also denoted by any one of the following. So in the textbook, the notation is okay. It's either plus or a minus. So let me see. And this is why I don't like this notation. From the right? Okay, from the left now. It's a minus. You put a minus there. And then you look at some other book, and they switch the notation. So, so you can write this, or this is slightly better, I think. As x goes to rho, let's say that x is less than rho. Now you don't need to remember if minus represents this way or this way. F of x, and the notation is, yeah. What I really like is to use the additive structure here and really say, as epsilon goes to 0, epsilon positive, and f of rho minus epsilon. Okay? These are all the same idea. A nice thing about this is that if I have a function that is defined, let's say, everywhere on an interval except at a point, it is, so the limit at that point exists if and only if the, I guess, left limit and the right limit match. Limits match. So this is the so-called one-sided limit, or the left limit, because you're approaching from the left. So I'm going to leave that as an exercise. Okay, get rid of that. Let's say again, I have minus infinity, and then lambda, and then I have mu for middle point, and then a rho, and then positive infinity. Let's say that f is defined on, well, lambda rho, open interval, except at this middle point somewhere, okay? Taking values is some metric space. Then, oh, now again a y star. Then the limit of f as x goes to mu, this problematic point, in the interval lambda rho is y star if and only if, well, the left limit and the right limit exist and they are equal to the same value. So as x goes to mu, x in lambda mu, f of x equals y star, which is equal to the limit of f as x goes to mu, where x varies in mu rho. What is the picture accompanying this exercise? Well, the picture is this. So I have my vertical space, y. Here's lambda, here's rho, somewhere here is mu, okay? Now, f is not necessarily defined on mu, but it is defined in between here, and it is defined here. And somewhere here is y star. This is my target, okay? Now, I'm not saying that f of mu equals y star. That's going to be important when we start talking about derivatives, but it doesn't need to be defined there. What I need is that as I'm approaching mu on the subset where f is defined, I want to have a unique limit. That's what this means. And so maybe the graph of f is like this, and then something like this maybe, okay? This says that this limit, the limit of f as x goes to mu is y star if and only if the left limit, which is this point, matches with this right point. Okay? What could have happened is something like this. Let's say that this guy approaches to this point, but then from this side it approaches like this. Okay? Here, limit as x goes to mu does not exist. So there's a jump discontinuity. Okay. Now it turns out that there are different types of discontinuities. There's what is called removable discontinuity. In this case, for instance, if you look at the red graph, even though it is not defined at this point, and in particular, it is not continuous, technically speaking, well, you can fill it. You can just add this point, and now you have a continuous function. That's why this red situation would be a removable discontinuity. In the blue discontinuity, you cannot do that. It's a jump discontinuity. You cannot just like fill in the blank to get a continuous function. And then there's a third one, which is sort of like this oscillation problem. It's what's called an essential discontinuity or singularity and stuff like that. There's a bunch of sort of terminology about this, and then you look into the sizes of these discontinuity sets and stuff like that. Probably they're too advanced for this class, so we're not going to discuss it, but maybe if you have time later, we can have a look at it. Certainly, if you take more advanced analysis classes, you're going to encounter these ideas. Any questions? Okay. So differential calculus. Derivatives. I want today to be a relaxed class because we're going to try to broaden our horizons a little bit before going into the technical details. So differential calculus. Let's think about this. What is a derivative? Any guesses, any ideas? Coming from, let's say, single variable calculus or whatever, or multivariable calculus. You've seen a bunch of different derivatives. Partial derivatives, I don't know, Jacobian. But what is it? How would you sort of, what is the first approximation to the notion of a derivative? Slope, okay? That's one. Slope. And that is the first thing that you learn, right? Like it's this number, but it is a slope of something. What is it the slope of?
The rate of change.
Yes, yes. It's approximately the same, but yeah, instantaneous rate of change. This is also the same. So instantaneous. In a second, in fact, I'm going to rewrite this in a different language that is more evocative. But there's something more sort of geometric. It's a slope of something.
Maybe the slope of the graph of the function? the slope, but it's more analysis-y.
Yes, slope of the tangent line, right? That's what I was looking for. So in other words, really once you have the derivative, you also know the tangent line, okay? So let's write it like this. How did I write it here? So tangent line. Now in one variable, in single variable, these two things are the same pretty much, because if you know the slope of whatever, well, you have your function here. Let's say that you're looking at the derivative at this point. Well, you know through what point this tangent line is supposed to pass. So in other words, so this line has the equation y equals ax plus b. A is the slope, and b is essentially the information f of x, right? Now, let me interpret these a little bit. So how many of you have seen this idea that it's the slope of the tangent line, right? Like this is the linear approximation of the function. That doesn't work globally, but locally it works, right? So this function, I cannot pretend, is the same thing as this line globally, but locally, in other words, for sufficiently small values here, I can pretend that this function is actually a line up to an epsilon, but I can bite the bullet and take that error and try to do something with it. So when you really start thinking about this, or when you get more experience about this kind of stuff, this is sort of how you want to interpret this. This really is about local approximation of the more complicated object using models that you deem are simpler. In this case, you have sort of like a wiggly thing. It's a nonlinear function, and you're approximating using lines. Lines, you say, are simpler objects, and I'm going to try to locally approximate my complicated thing using the things that are simpler. So this is local approximation via simpler models. In a single variable setting, simpler model just means a line. Y equals ax plus b. I'm trying to find the best y equals ax plus b that approximates, that fits my function. Okay. Now you could say, why am I thinking linear functions or affine functions, y equals ax plus b's, to be the simpler models? Well, certainly, I mean, it's sort of like it comes from intuition in a sense. It's like, because to describe a line, all you need is two numbers. If you can store two numbers, you have the whole line. But to store a more complicated function, it's not that simple, right? And you sort of like a general formula, whatever. Imagine sine of x. How are you going to describe it? So, but you don't need to stop there, of course, is what I'm trying to say. Maybe once you're done with sort of finding the simplest model, which is sort of this y equals ax plus b, then you can ask for, well, what is the best parabola that fits the function like that? And we're going to do this later at the end of this class, actually. This leads to this idea of a Taylor approximation. So you can look at the best line that fits the function at a point, then best parabola that fits the function, best cubic, best quartic, and so on. Okay? And if you can go all the way to infinity, that's even better. And in fact, if you can sort of write it as a convergent series, that is the idea of Taylor expansion of a function or the Maclaurin expansion, whatever. So that's the best type of function in a sense. These are what are called real analytic functions. But we're going to get to that later. For now, we're just trying to understand what is a sort of underlying idea. Okay. So this is the first idea. And as opposed to this notion of the slope, I would suggest to you that this is the stronger interpretation. The tangent line is a geometric object, okay? So in a sense, even if you didn't know anything about numbers, if I were to give you a ruler, you could draw the tangent line. And in a sense, you would have you would have an idea as to what the derivative is. You wouldn't understand it as, well, a number, which is very convenient, of course, but you would have a very strong understanding of the geometry behind, right? And you can solve a lot of problems with just being able to draw the tangent line. Therefore, slope, this notion of the derivative as a number, is a much weaker understanding. So this is the stronger interpretation. This is the weaker interpretation. There are more interpretations of the derivative, but these two are the fundamental ones that we're going to be interested in. And so what your colleague suggested a while ago is that it's the slope, in other words, is the instantaneous rate of change. So, in other words, it's something about the, what is it? Rise over run, okay? I want to say that this weaker interpretation is all about controlling rise over run. Now, whenever you can take this limit, right, so there's a ratio and then you take the limit, insofar as that exists, in other words, whenever the derivative exists, you have this number here. So there's a number here in single variable. But really, it turns out that the idea that is sufficient and that scales up to higher dimensions and more abstract settings is, well, upper bounds and lower bounds of this value by some of their numbers. Okay. And so maybe we should talk about this a little bit. So here's a function. Again, I'm going to draw a generic function like this, something like this perhaps. And then let's say that I take this point and I'm looking at the derivative here. Maybe I want something like this actually. Okay, it's a better picture. So what is the rise over run? Right? So rise is the change in the height, and run is the change over the horizontal. So what do you do? You take a small triangle here, or maybe a large triangle if you want. Then you can approximate. So this is the rise. This is the run. Okay. Let's say that I have an upper bound over the rise over run. Okay, let's say that I can bound it from above. Now, what does this mean? This means that really I draw, let's say, a cone like this. Okay, so this is a horizontal line. this is the case where you break even. And the slope here is c, and this is minus c. So this is saying that if you can control rise over run by c, by some number, that means that you can control the function in such a way that you know that at this point, as you're moving this way, let's say, it's not going to escape this way. It's going to only escape in some direction that is inside this cone. And likewise in the backwards direction. So somehow, being able to control the rise over run from above corresponds to discarding certain parts. Okay? You're saying that this function doesn't grow too fast. So the graph doesn't become too too vertical. Okay? And so if you have any background in physics, this should remind you of things like the causality cones and stuff. They are related ideas, of course. This is much simpler. Any questions about these so far? Now, how many of you have heard of this theorem called the mean value theorem? Okay, what does it say?
The slope must take the mean value at some point.
Right, so it basically says this, which we're going to prove. If you have a function like this, well, look at the global rise over run. It says that as you're going from here to there, insofar as your function is differentiable, there's a point where this global rise over run is actuated, actually. That's one way of stating this. There's a way of stating this using integrals and stuff like that, which we're going to get to once we start talking about integrals as well. But that's fine. Now, the issue with this, I mean, it is correct, of course, what your colleague is saying. In general, like I mentioned here, you end up not being able to say the rise over run is exactly this, okay, in higher dimensions. And so it becomes sort of like misleading to think of rise over run as a number that you're going to have specifically. It's better to think of it as something that you can upper bound if you have differentiability. So for now, though, let's just say that this is a stronger interpretation and this is the weaker interpretation, essentially by way of the mean value theorem. Okay. And now we have a conundrum. Okay. So far, we were talking about sets and logic, proofs, and continuity and stuff. And often I was able to rephrase a lot of things in the abstract setting of metric spaces, partially to improve your mathematical maturity, and partially because many of the arguments that we were using were not specific to single variable calculus. Okay. Now it turns out that when you actually start talking about calculus, you cannot really immediately talk about this stronger interpretation of derivatives in the context of abstract metric spaces. Fundamentally, because in order for this stronger interpretation to work, the underlying space on which the function is defined already must have some local models. Okay? So in this case, my underlying metric space should be something like, oh, maybe it's like it has like local, it looks locally like a line or something. Now there's a mathematical object that corresponds to this, which is called the manifold, a metric space with nice local models. But it turns out that defining it is rather cumbersome, at least at this stage. And if you take more advanced classes, something like differential geometry, you're going to end up needing to learn what a manifold is. But I don't think at this stage it is reasonable to describe it. So many of the things that we're going to discuss when it comes to differential calculus is going to be specific to single variable calculus, even though there are generalizations. Okay? I just don't want to define it. So need manifolds. Instead of metric spaces, I need manifolds. And manifolds are basically, or manifold is basically a metric space that has local simple models. So in this class, we're going to be looking into single variable differentiability. So we're going to look at functions defined on an interval and stuff. And in the sequel class, you're going to look at functions that are multivariable, that is defined on Euclidean spaces and stuff. So that's going to be sort of the local model there. This, though, the weaker interpretation, I can make sense of in the context of metric spaces. Because it turns out that instead of thinking rise over run as, the rise is the length of this line segment and the run is the length of this line segment, well, you can just look at the distances. In other words, we can make sense of this in the context of arbitrary metric spaces. And so this is what leads to this idea of a Lipschitz function. Okay? So a Lipschitz function is a function that is basically differentiable, not quite, but in this weaker sense. Okay? In the context of metric spaces, you don't have local models. You cannot really talk about actual differentiability. The next best thing is functions where you can control the rise over run. Okay? And so here's the definition. And in fact, let's be slightly more general and define Hölder functions. Let x and y be metric spaces and f be a function from x to y. Let me let theta to be a positive number. Okay. Now I'm going to say that f satisfies a theta-Holder estimate if the following holds. Well, instead of writing rise over run, I'm going to take run and multiply it on this side. It's going to be an upper bound. If there's a number such that for any 2 points in x, I have that the distance between images of these 2 points under f is bounded by c, this constant, times the distance between them to the power theta. Okay. It looks kind of bizarre, but this is a very common definition. It's also in the textbook, actually, as part of a problem. So what is going on here? Well, one thing is that any function that satisfies this estimate has to be continuous. Okay? Because if I have and x bullet converging to x star, well, the distance between their images is bounded by some multiple times the distance between these two to some power. But as this sequence approaches to this distance is going to decay, which means that the distance between the images are going to decay. Okay? So any theta-Holder function is continuous at the very least. Okay? It's in fact more. It is uniformly continuous, but we didn't talk about uniform continuity that much, so I don't want to spend too much time on that. And in a second, I'm going to give you an example. Let me finish this definition. If theta is 1 here, so that you get the actual rise over run instead of the run to the power theta, you call it a Lipschitz. So 1 Holder is the same thing as Lipschitz. Okay. So here's a fundamental example. Well, let's start easy perhaps. Let me let f to be defined on the interval 0, 1, taking values in the reals. Well, let's let f of x to be root x, square root of x. In other words, f is x to the power 1/2. Now I'm going to leave that to you as an exercise that this satisfies a theta-Holder estimate with theta exactly equal to 1/2. Okay? And in fact, if you were to generalize this, exercise. For any alpha and beta, let's say positive, and let's say that alpha is less than beta, f of x defined as x to the alpha is alpha Holder but not beta Holder. Okay. Now what is going on here? Somehow you want this theta to be as large as possible. In other words, the larger the theta is, the better the function becomes, the more control you have. Okay, so let me write that. The better control one has over the rise over run. Hence, the function becomes better. It becomes more regular. And here's the idea behind this. And then we'll finalize. We'll finish the discussion for today. So again, imagine I have my function and so on, and I'm looking at what is happening at a point. And I'm trying to look at this cone, okay? So I'm drawing this large, but you should really think of it as something small. So this is when you have alpha equals 1. So this is the diagonal. Something like this is when alpha equals root 2. Okay, and then, 1/2. And then this is 1/3 and so on. And I guess we should call this theta, the exponent. And this, and this. So you see, the smaller the theta is, the more vertical your controlling cone becomes. It becomes like more like bulbous this way, which means that if you have theta equals 1/3, it's much easier for the function to be going up. Okay? If you have theta equals 1, then you cannot grow like this. You have to be less crazy, let's say. So this is the main idea. As you decrease theta, the cone becomes more and more bulbous, which means that you're losing more and more control, which means that the function gets worse and worse, quite possibly. So you want to make theta as large as possible. And typically, when theta is 1, that is to say, when you have the Lipschitz case, that's the best case in general. Okay. This, even though it's not a very complicated concept, it takes a while to understand, but it's very useful, comes up everywhere, so I think it would be good for us to think about this a little bit. And I think that's it for today. We'll continue on Friday. Thank you. Okay, let's start. Good morning. Happy Valentine's. Very exciting stuff, because today we're going to start talking about differentiability in a proper manner. Really, as I was preparing the lecture, it's just so beautiful, at least to me. So it's like everything works, and now we have like more tools to play with instead of this abstract stuff. Continuity is like something more malleable compared to differentiability and so on. Okay. Yeah. So let's start with the definition that probably all of you have seen before. In a second, I'm going to sort of rearrange it in a way to make it slightly more different, perhaps. But it's going to be very convenient to have different forms of this notion of differentiability. So where we had talked about on Wednesday this weaker interpretation of the derivative in terms of this Lipschitz or Hölder properties, that was about controlling the rise over run. Now I'm really focusing on the first interpretation, the stronger interpretation. Here in this representation, it is not apparent, but in a second it's going to be more apparent. Okay. So I take, as usual, an open interval and a function taking real values defined on it, and I take a point x star in my interval I. And I'm going to say that my function f is differentiable at x star, well, if the following ratio, the following limit exists, right? So I look at the rise over run, and I take the limit as x goes to x star. Now, this function is not necessarily defined at x equals x star, because the denominator is, well, it is 0, so it is not defined there. So maybe I should say I take away x star, and I want this limit to exist as a real number. I don't allow it to be infinity or minus infinity. And in this case, this limit is denoted by f prime of x star, or df by dx of x star. And this is like common. And this is called the derivative of f at x star. And it's called the derivative of f at x star. Okay. How many of you are familiar with this definition? I hope all of you have seen this. Yeah. Okay. Okay. Now, just like continuity, recall that continuity of a function we defined first at a point, and then we said if the function is continuous everywhere, or at any point, we call it continuous. Same thing holds, same sort of like mentality goes for differentiability. If the function is differentiable at any point whatsoever in x, x is I, of course, here, then I'm just going to call the function differentiable. And in this case, you see now what I can do is I can vary this input value in this derivative expression. And then that would give me f prime, or df by dx, which I can think of as a function in and of itself from the interval to the reals. And this is again called the derivative of f. It's a function. Let me write this. If I have two functions f and g defined on I such that f prime equals g, so that g is the derivative of f, well, I can also say that f is the antiderivative of g. Okay, that's going to be important later when we start talking about the fundamental theorem of calculus. So I have two functions f and g that are related this way. If you want, this is a differential equation, because I'm saying that the derivative of f is this other function g. Then is an antiderivative. Let me write it here. Antiderivative. Of g. Sometimes you can also see the word integral already. You see, we haven't defined the notion of integrability, but we're getting closer to the fundamental theorem of calculus, because ultimately, the moment we define integrals, we're going to try to define it in such a way that integration is the inverse operation in a sense of differentiation. Now, why am I using here the indefinite article n, antiderivative? Yeah.
You can have infinite antiderivatives just differing by a constant.
Right? Because when you're trying to sort of take the integral of something, right, you always have plus a constant c. That's why it's an antiderivative. Just because two functions are such that, let's say, f and h are such that f prime equals h prime, you cannot say that f is equal to h. If you have some additional condition, if you have some additional information about the function, for instance, in differential equations, you would have something like an initial condition or something, then you can say that, oh, in fact, f is equal to h, if the initial conditions match as well, and so on. We're not going to get to that, of course, but if you have taken differential equations, you're probably familiar with these types of ideas. So any questions about this? Up to now, everything is fairly standard. Now, what I'd like to do is, I would like to rewrite this in different forms, because given, in different situations, different forms of this notion of differentiability turn out to be more useful, okay? So, okay, well, maybe even before that, we should define functions or function sets. If f is differentiable everywhere, so that f prime exists as a function from I to R, and if, additionally, if f prime itself is a continuous function, so that f has a continuous derivative, I'm going to call it continuously differentiable. I'm going to say that it is in class C1 as opposed to C0, which just meant continuity. If f prime is in C0, I'm going to say that f is in C1. Then f is continuously differentiable. Or of class C1, and the set of all such functions, in other words, the set of all continuously differentiable functions from the interval to the reals, I'm going to denote it by C1, C to the 1 of I comma R. Okay, so we were using C to the 0 to represent continuous functions. Now we have C to the 1. That's another set. It's a subset of continuous functions we're going to see in a second. Because it turns out that any differentiable function is continuous. But it's going to be important for us to understand this notion. And of course, we can go to higher order differentiability. Because I can also ask, for instance, not only that f is differentiable, not only that f prime is continuous, but in fact I can ask f prime itself to be differentiable. And then I can differentiate f prime to get f double prime and so on, right? So it's higher order derivatives. You're familiar with these ideas. But we're going to get to that later. What I want to do now is to paraphrase this, okay, in a few different ways. F is differentiable at x star. We said that this is the same thing as saying that, well, limit as x goes to x star, x is in I, take away x star of this ratio. Well, let's use the notation as well, f prime of x star. Okay. Well, what I can do is, instead of writing it this way, recall on Wednesday we had talked about sort of different ways of writing this limit business. And in this case, I, the interval, I have addition on it. So instead of saying x goes to x star, I can take an h. Okay, that's a familiar form of this. So I can write it like so. Limit as h goes to 0 of f of x star plus h minus f of x star divided by h equals f prime of x star. Are we all comfortable with this conversion? Right? Because what I can say is that, well, instead of looking at x minus x star, I can do a change of variables if you want. Let me just call x minus x star h. Here x star is fixed, x is variable, which means that now h is going to vary. As x goes to x star, h goes to 0. And of course, if h is x minus x star, then x is x star plus h. So this is the sort of conversion that allows me to switch from here to there. Now, in calculus, typically we're used to doing this change of variables explicitly in integrals. For instance, think about like U substitution or something. But you can do this whenever you have sort of bunch of different letters and you're trying to change one set of letters to another one. So I can do this. But then what is this? I can say that, oh, this limit, so the limit of this goes to this if and only if the distance between them, in other words, the absolute value of their difference goes to 0. Again, by just taking this to the other side and so on. Limit as h goes to 0 so I'm going to have the ratio here equals 0. So this is a number because I'm assuming that it is differentiable here. I took it to the other side and then I want to simplify this expression. So I'm going to multiply this by h in the numerator and h in the denominator to get this expression. Okay. I'm just rewriting the same thing. Okay. And in fact, what I can do is, because what might happen is that in this definition, I'm not saying h is positive or negative, okay? Because ultimately, I need h to, I have to allow h approaching to 0 from the right or from the left. And so the denominator here is going to be positive or negative. So it has two cases. So what I can do is, just so that it is slightly more convenient, I can put absolute values here. So that now the numerator is a non-negative number. The denominator is a non-negative number also. Okay? So this is slightly more convenient to use. Now, this is the form where this first interpretation is the most apparent. Okay? What this is saying is that I have this function f. I'm trying to understand how it behaves near x star. Well, to understand this guy, what you can do is you can try to approximate it using a simpler function. Now note that this is a function, if I were to think of the independent variable as h, because x star is fixed, at least for the definition of differentiability at x star, think of this as a function of h. So this is a function of the form, well, ax plus b. If you were to plot this against h, that would be a line, right? Of course, it's exactly the tangent line, if you think about it. Right? Because if h is 0, this is at f of x star, and as I'm varying h, I'm moving in this slope. So maybe let's draw this, because this is a very important point. Even though it is not super sophisticated, it is very important to understand this. So let's say that, well, L of h, L for line, equals f of x star plus f prime of x star times h. Now I want to plot this against h, not against x, okay? So in a sense, I am trying to approximate this function, but the input values is different. The inputs of this function, I don't want to think of it as x. I want to think of it as h. Okay, so this is h against L of h. Now what does this say? This says that at h equals 0, I'm at this point, f of x star. And then the slope is supposed to be this guy. And if I know where a line passes and what its slope is, then I know everything. I can draw the whole graph. So the slope, rise over run, whatever. Okay. Any questions about this? The variables get confusing because we have the variable x, which possibly we're going to move, but we have another variable, h. Okay? When you take the derivative, you forget about the h, of course, because this expression, once you take the derivative, is independent of h. But it's still dependent on x star, if you think about it. But what I'd like to say is that here, the original function f is the complicated object I'm trying to understand. And this L is the local simple model that I'm using to approximate. In other words, to understand f slightly better. Trying to summarize it, simplify it. Okay? Complicated object. L here is the simpler model approximating f. Of course, near x star. I'm not saying that, oh, I can just think of f exactly as L unconditionally. So globally, you cannot do it. But locally, right, so you sort of like restrict your scope. You say, I don't want to understand f in general. I want to understand it near this specific point that I chose. And then once you restrict your scope, you have more power because you have a model. At least that's what it means for a function to be differentiable at this point. Okay? Now, here's something that I'm going to do. This is also equivalent to the following expression. So I'm going to continue here. This you might have not seen before. Possibly most of you did, or some of you did. This is equivalent to saying that the numerator, I'm going to write, okay, I think I'm going to delete this. Plus f prime of x star times h in brackets. This is the numerator. I'm just going to say this is equal to lowercase o of h as h goes to 0. So this is what is called the little o notation. How many of you have seen something like this before? Okay.
Is there a way to write that without it getting confused for 0? I guess maybe include like a little swirly.
Yeah, you can. Yeah, I guess you can put things, maybe something like this. Yeah. So this is one part of what is called asymptotic notation. So, for instance, in computer science, when you're trying to analyze a certain type of algorithm for how efficient it is in terms of time complexity or space complexity, whatever, you start using notations like this. Because, for instance, you want to have sort of like, you want to have a sorting task that depends, so you're trying to sort 10 different items, and you have a certain algorithm. Well, quite possibly, if you try to sort 100 items, you're going to need more time. So somehow you want to give a number You want to say something that is independent of the number of things that you're trying to count or you're trying to sort. So you say, okay, let's say that I'm trying to sort n different items, and this is my algorithm. How many steps does my algorithm require if I need to sort n items? And then you look at how that number grows as you increase n. So you're looking at asymptotics, okay? That's the idea. This is also used in engineering, physics, many other things. It's going to be very convenient for us. Of course, you can keep using epsilon deltas, but once you get the hang of this little o notation, and there's another one which is called big O notation, things are going to be a lot faster, okay? This is perfectly rigorous. I'm going to give you the definition in a second, but I want you to get comfortable with this. And there's going to be a problem in problem set 5, all about this little o and big O. Okay, so here's the definition. Oh, let me just say this as well. Instead of writing it like this, what you can write is also this. Okay, because this is the function that I'm trying to understand. This is the approximation. So I'm going to send this to the other side. That is allowed, okay? F of x star plus h equals f of x star plus f prime of x star times h plus O of h as h goes to 0. And the way you're supposed to read this is f of x star plus h equals f of x star plus f prime of x star times h plus O of h. Okay, so this is supposed to mean that this is a function, so what this is that you're saying that up to higher order terms, so this is the 0th order term, this is the 1st order term, you're saying up to higher order terms, f of x star plus h is this line. That's what you're saying. So you have higher order terms, so h squared, h cubed, and stuff like that. But then you say to yourself, well, I'm going to take h to 0. Well, h squared is going to decay faster compared to h. And so is h cubed and stuff like that. And you're saying that as a first approximation, in other words, when I'm just looking at approximating f to the first order, I don't care about higher order terms. That's what you're saying. Later on, we're going to start caring about the higher order terms, and then we're going to look at O of h squared and so on. That's going to lead to Taylor approximation. So you can write it like this. F of x star plus h equals f of x star plus f prime of x star times h plus higher order terms. This is slightly more vague, of course, compared to this, but they're pretty much the same thing. Now, here's the definition of big O and small o, or little o. So I said these orders of magnitude, these are what are called, are used in computer science, but in general, it is used in any area where you have a bunch of things to count, but it is basically not perhaps possible, or even if it were possible, it's not that illustrative to actually give the actual number, okay? You just want to look at the asymptotics. You want to have an approximate idea. For instance, in statistical mechanics and stuff like that too, you use this type of stuff. So, orders of magnitude. So in a sense, you can think of it like this. These are really rigorous ways to be vague about what you're doing, okay? So this is somewhat paradoxical, but we do this all the time in math. So let X be a metric space. Let's let f be a function from x to r, and beta is another function from x to r plus, let's say, or positive numbers. That's how I defined it. And let's let x star to be a point in X. So I'm going to say that f of x equals big O of beta of x as x goes to x star. So this is how you read it. F is big O of beta as x goes to x star. If, okay, this is how you say it. There is a number c. Let me see. Okay, yeah. There's a number c and a delta, positive, such that for any x in X, if the distance between x and x star is bounded by delta, then f of x in absolute value is bounded from above by c times beta. You can take x star to be infinity too, in which case you're taking larger and larger things and so on. So what does this mean? This means that as you're getting closer, as you're taking x closer to x star, you don't know what f is exactly, but you actually have an upper bound at the very least. You have a control. And then I'm going to say that f of x is little o of beta. Let me write it here. Well, I'm just going to abstract out this definition. In other words, I'm going to define little o in such a way that this equivalence between what I wrote before about derivatives and this is true. Okay. Now we've been doing this. We did this a couple times in this class. So we have sort of like an idea, and then we rewrite it in some other way, and then we define something so that that rewrite is actually a rewrite. Right? It's not something new. So f of x equals little o of beta as x goes to x star little o of beta as x goes to x star if, well, it's slightly stronger than just the bound. What you want to say is this. F of x divided by beta of x as x goes to x star is 0. Okay, because this was, you see, this came from the definition of derivatives. So what did I do? I had this in the denominator, and I took the limit. And I wanted that limit to be 0. So I'm just writing that. If limit as x goes to x star of f of x divided by beta of x, let's put this, doesn't matter, equals 0. Okay. So what does this mean? This means that as x goes to x star, in this case, for instance, h decays. So the denominator decays, but I want the numerator to decay faster than the denominator decays. That's the only way this ratio goes to 0. If it didn't happen, then this would be either a positive number or it would go to infinity. Okay? So you want beta to win over f. Okay. Any questions about these? Okay. Now you're going to see in a second why these are so useful. Because ultimately what I want is that now that we've been dealing with epsilons and deltas, and even though we could keep using epsilons and deltas, they're not very convenient, okay? So we want sort of like a higher order idea that is related to epsilons and deltas, but that allow me to sort of basically argue rigorously without worrying too much about these epsilons and deltas. Sometimes you do need to sort of open up and use epsilon and deltas and all that stuff, but if possible, you want to avoid it, right? It's not nice. It's cumbersome. Okay. So here are some exercises actually. So let's say that I have a polynomial of degree n. Let's say that the top leading term is not 0, so that this is indeed degree n. Then I can say, for instance, f of x equals O of x to the k as x goes to infinity. Okay. Now what am I saying? This is saying that up to a constant, I can just pretend that this guy doesn't have any lower order terms. Because when it comes to the growth, what's going to matter is the highest order term. So for instance, this also allows you to sort of simplify the situations. Let's say that you have a statement about polynomials and stuff, but you have all these like middle terms and stuff. When you try to compute something, you're going to realize that, oh, you know, even though it's not a big deal somehow, when you're trying to compute it, it's like things get cumbersome. So what you can say is that, oh, this polynomial, even though it might have lower order terms, I'm just going to pretend that it's just a monomial because I'm perhaps interested in what happens asymptotically or something. I can also say that f of x equals lowercase, oh, this is uppercase, this is lowercase, little o of x to the, oh, this should be n, of course, highest order term, this. Little o of n plus 1, why? Because this guy cannot grow faster than x to the n. So if I were to divide it by x to the n plus 1, well, the denominator is always going to beat f, which means that the ratio is going to go to 0. Okay? Any questions about this? Yes?
Can you go over the difference between big O and little o again?
Yeah. So here's an example, okay? Say I'm saying that f of x is big O of 1. Now what does this mean? This means that as x goes to infinity, let's say. Typically in applications, people don't specify this because it's typically apparent from the content where you're taking x. Because like if you have an algorithm and n is the number of things that you're trying to sort, you're not going to take n to 0. You're going to take it to infinity. But let's be explicit here. So I have the graph. Now what does this mean? This means that there is some constant. So beta here is 1. Okay? So you don't have this. There is some constant such that after, if you're sufficiently close to infinity, in other words, if x is sufficiently large, you're going to be bounded by that number. So there is a c. You're going to positive infinity. This is your bound. Initially, this might happen, but if you wait long enough, it's not going to be bounded by this. This is big O. Okay? This means this guy is asymptotically bounded. C could be 10,000, by the way. You don't know what C is. You know that it exists, though. Let's look at the little o of 1. Right, because let's say that you're sort of looking at an algorithm, but maybe for the, I don't know, your algorithm doesn't perform that well for, for the first n equals 15, let's say. There are better algorithms, perhaps. But as you take n larger and larger, then your algorithm starts to shine, perhaps. I don't know. That's sort of what you're trying to get. And why is this important? Because, well, big data and everything, right? Like, nothing is small. Everything is large, and what matters is to be able to control large things. So if you're not performing that well for small things, then that's not really a problem. Okay, so that's the first example. Second example is, let's say that f of x is equal to lowercase o of 1 as x goes to infinity. Now what does this say? This says that, again, beta is 1. The limit as x goes to infinity of f of x equals 0. Do you see this? Again, initially, bizarre things can happen, but then you're going to converge to 0. Which one is stronger? Is this a stronger statement than this, or vice versa? Let's think about sine of x. Is this big O of 1? It's bounded. Oscillates between plus 1 and minus 1. Is it little o? It doesn't converge. Cannot converge, okay? So saying that the function is little o is stronger. Okay. And of course, if a function were little o, then it would be big O of 1. Why? Because if a function converges to 0 asymptotically, well, asymptotically I can say it is bounded by 1. Okay? Or some number, whatever number. Does this sort of make sense? Yeah. Now, typically, because perhaps it is not as rigorous in a sense as, well, it is rigorous, but let me put it this way. It is easier to make mistakes with these orders of magnitude compared to making mistakes with epsilons and deltas. But if you're careful with them, they're perfectly rigorous, and they're very convenient things. And you might as well start learning them, start learning how to use them now, because they're very useful indeed. And people use them all over the place. Maybe not that much in pure math, but even in pure math. Okay, any questions about anything here? So here's the first theorem. If I have a function that is differentiable at x, that's x star, let's say, it is also continuous there. Okay, so differentiability is a notion that is stronger than continuity. Same setup as before. If f is differentiable at x star, then it is continuous there. As a consequence of this, the set of continuously differentiable functions on I, on the interval, is a subset of the set of, continuous differentiable is a subset of continuous functions. Hence, C1 of I, comma R is a subset of C0 of I, comma R. Okay, because C1 means that it is differentiable at the very least everywhere. This is more, but still at the very least that. So the proof goes like this, okay? So what do I need to show? Okay, let's use this O notation. I know that f is differentiable at x star, which means that this guy is f of x star plus f prime of x star times h plus higher order terms. Okay? Now, as h goes to 0, this is a number, which means that this guy goes to 0, and this guy also goes to 0. By definition, this has to go to 0, if you think about it. Which means that this converges to this as h goes to 0. Okay? And that's the end. Okay? This is perfectly valid. It's a rigorous proof. Okay? Doesn't feel like it, I know, but I want you to get comfortable with this. The main thing here is understanding why this little o of h goes to 0 as h goes to 0. Okay? Little o of h, recall the definition, is something that decays faster than h decays as h goes to 0. Okay? In particular, it has to go to 0. Okay? This is the main thing to understand. Why is it the case that as h goes to 0, O of h goes to 0 also? Little o of h. Okay? You can use epsilons and deltas and stuff, and that's what they use in the textbook as well. But I think you understand sufficiently well how to use epsilons and deltas, and it's good to have an understanding of this higher order expression. Maybe we should do the epsilon delta proof also. Should we do sort of like a more classical, more conventional proof of this? Yeah, let's see. Second proof. It's going to be a lot longer than this because this little o is doing a lot of work behind the scenes. You see, in computer science too, you have different languages, and some of them are like lower order, right? And some of them are higher order. Some of them, something like C, doesn't do memory management for you. You have to do it yourself. You have to malloc everything and so on. But if you do Python, you're good. But of course, Python, that's why, you know, if you're trying to make a computer game, you don't use Python. I mean, you might, but it's perhaps better to use something closer to C because you need more efficiency. So epsilon deltas are more efficient, in fact, because they're lower level in terms of language, but at a higher order, at a higher level, it's, you know, something like this is faster. Second proof. So what do I need to bound? I need to bound this distance between these two, as h goes to 0. This is what I'm trying to control. Okay? Now I'm going to try to get the phrase, get the expression for the differentiability by adding and subtracting. So this is this minus this guy, and then plus f prime of x star times h, and then I need to add one more. So this is in absolute values. And I'm going to split this guy to get this. This is the first part, plus this term. Okay. Then I'm going to divide and multiply by h. So I have this minus f of x star plus f prime of x star times h divided by h, then multiplied by h, and then this is f of x star in absolute value times h in absolute value. Okay. Here's the solution, the end. I know that as h goes to 0, this goes to 0, because I assume that f is differentiable. This is a number. This goes to 0, and this too goes to 0. That's the more conventional proof of the same statement. As you see, it's a lot more advanced, or it's a lot more involved. They are both perfectly valid, okay? They are both rigorous. Okay, that's it. Thank you. Have a nice long weekend. We don't have class on Monday because of President's Day. We're going to start on Tuesday.